This is Mr. Sitta. We're studying Chapter 5 in Brown-LeMay, Thermochemistry. This is Section 5.4, and 5.4 deals with enthalpies of reactions, okay? So if I give you a reaction like the one in the sample, ethanol C2H5OH plus 3O2, combustion reaction, so it produces 2 CO2 gas plus 3H2O. Okay, now if I was to tell you that the delta H of the system, now delta H for a reaction, the change in the enthalpy for a reaction is going to be the enthalpy of your products, H products, minus the enthalpy of your reactants. Okay, so if I was to look at a potential energy diagram for this, okay, here's my H, and that's my potential energy. Here's your reaction progress. Now, they give me the delta H on the problem. It's negative 1235 kJs. As soon as I see that it's negative, I know that this is exothermic, that the heat's going to be released. So if it's exothermic, I know that the reactants are going to be higher than my products. So here's my products. Here's my reactants. And the reactants are C2H5OH. And my products are 2CO2 plus 3H2O. Okay. Well, how much higher are they? If I look at this equation, they're at 1235 kJs higher. So the delta H is negative. It dropped down 1235 kJs. Okay. Now, you always have to invest energy, and then you go down to your product. From here to here is EACT. That's my activation energy. Right at that point, that's where things are at their highest in potential energy. It's called an activated complex. I'm not really going to follow that. And one interesting thing I might mention, this would be plus O2, 3O2. This is the energy I have to put in to break bonds. This is the energy I get back, even from up here, in releasing the bonds. Okay, but the total change in energy, products minus reactants, is here to here. Okay, now, this sounds very complex. If I was to ask you to write a thermochemical reaction, okay, that sounds very complicated. Well, all you're doing is putting your delta H in there. Now the sign is just telling you whether it's coming or going. If it's a negative, it means it's coming, it's going, it's being released. So what I can do here is I can put plus 1235 kJs. Now what happened to the sign? Well, that sign was just telling me that it was a product, that it was released. So the sign tells you whether it's endo or exothermic, but it's not really that there's a negative amount of heat, it's just that it's being released. This is missing that much heat. And so it's kind of an accounting. And if I was to flip this reaction and say, let's take 2 CO2 and add 3H2O and then create ethanol and 3O2s, this would go to the left-hand side, plus 1235 kJs, because heat is conserved. But the delta H for this reaction now, instead of being negative, now it's going to be positive. Positive means that it's a reactant. 1235 kJs. So just get used to the fact that the sign is just telling you whether it's coming or going. So I can do stoichiometry with this, and here's the stoichiometry end of this. They don't have kJs per mole here, they just have an amount kJs. Well, I can read this into the reaction. This is per 1 mole of ethanol. This is per 3 moles of O2. This is per 2 moles of CO2, and 1235 per 3 moles. So depending upon which reactant I put, it's kJ per mole of that specific reactant. So here's the conversion factors I can use off of this equation. Conversion factors, that for CO2 I get 1235 kJs per, and then you actually use the coefficient, per 2 moles of CO2. Now that's a little discomforting just in the fact that when we do molar mass we don't use the coefficient, but when you use kJs you do use that coefficient. Other conversion factors, it's 1235 kJs per 3 moles of H2O. So the substance matters when you're using this. And the other one I can use, it's 1235 kJs per 1 mole of ethanol. And lastly, 1235 kJs per 3 moles of O2. Now, one thing, I didn't put any signs there because these would be no different than these. You know that in this reaction, these would be exothermic. Okay, everything here is exothermic, so it would be heat being reduced. In this reaction, it would be the amount of heat absorbed. So I would look at that at the very end. Okay, let's try some of these problems. And this really is simple stuff. I got a delta H that's negative. So it says, is it endothermic or exothermic? Well, it's negative. That's exothermic. Okay. If I give you this on a test, I'm always going to ask you to write this as a, I'm going to say write this as a thermochemical equation. And the secret to writing it as a thermochemical equation, CO2 plus 3H2O, is that if you see negative, you just put this on the right hand side and forget about your negative sign. It's now just an absolute value. Okay, if it was positive, you put it on the left. Now, which has higher enthalpy, the reactants or the products? Well, when I look at this and I see that this is plus 1273, well, these are higher. How high? Much higher? 1235. If you're thinking of it like money, like you need that much more energy to be equal. So the answer is the reactants are higher. That's if it's exothermic. If this was endothermic, on the left, it would be the products. Calculate, now here's your dimensional analysis, okay? Or dimensional analysis. I'm going to use the conversion factors that I just came up with. I'm going to use those. So calculate the amount of heat transferred. This is the Q. So Q is we're going to measure it in kJs in this case, because that's what I have is kJs. Calculate the amount of heat transferred when what was given to you, 68.5 grams. Now here, when I look at a mole map, somewhere here I have a mole map. You guys have been looking at mole maps all year. Okay, this is the bottom right here. This is going to be your delta H in kilojoules. So now you can go from grams of one substance and convert to kJs, from moles to kJs. Or you can go from a different substance and find your amount of kJs. So heat links these two in your mole map. Okay, So here I'm going from grams to kJs. Well, the secret is to go from grams to moles, then moles to kJs. But remember, the coefficient means something. All right, let's finish this off then. Okay. Labeling, absolutely have to. Okay, this is CO2. If you don't label, you're going to get it wrong. Okay, so I need to go from a gram to a mole, and that's CO2, which is 12 plus 32, so it's 44 per 1. So molar mass is always per 1 mole. That's where you don't want to get mixed up. Now this is a mole of CO2, so I want to go from a mole to a kJ, and here's where you're using this brand new conversion, the factor that we got. We can go from a mole of CO2, but now you have to use the coefficient. 2 moles of CO2 is equivalent to 1235 kJs. And I'm just going to forget about the negative positive sign. I mean, I'll put that on at the end if I figure out whether it's exo or endothermic. 68.5 divided by 44 times 1235 divided by 2. The mental analysis, 961 kJs. Bingo. Okay. Now look at the way they answered the question. They said the amount of heat transferred. So I didn't really need a sign. I can just say that the Q, the amount of heat transferred, equals 961. Believe it or not, if this went into water, I could find my mass of my water, my CP of the water, and find out what kind of temperature change I had. So I can go ahead but I'd have to take the Q then and put it into joules to put it into Q equals CP times M times delta T. So that can get linked up to calorimetry problems. Probably not going to go out there too far, being that the situation we're in, COVID-19. Now, if I was to put a sign on this, because this is exothermic, the sign I would put on it would be negative if they asked me for a sign. Okay, let's do the next one. Calculate the amount of ethanol. So I want to know the grams of C2H3,5OH, the grams of ethanol, to produce 625 kJs. And now I'm going to go from kJs to ethanol. I don't really like this one, and I'll tell you why. C2H5OH, I'm having trouble writing, because this is just a 1, and this is 20, 12, 35. Kind of wish I used oxygen for that problem, or water. Oxygen would have been 3, water would have been 3. And moles to grams, I need to get a molar mass on ethanol, 2 times 12, plus 5, plus 16, plus 1 more, 46 grams per mole of ethanol. Probably want to show you work. Okay, so we had 625 divided by 1235 times 46, and 23.3. Always calculate it and then compare it to the answer. I know I'm giving you the answers, but I only give you the answers so you can see if you're getting it right. Okay, that is good. We're up to 5.4. I'm probably going to assess you on this separately, and I'm going to assess you on calorimetry separately. Leave it simple. That's where we're at. Okay. Have a good night or a good day.